Linear operations can be defined as the mathematical operations of addition and scalar multiplication. In the field of real numbers, binary equations containing only addition and scalar multiplication are considered linear operations. For a real number line, any linear combination of multiple real numbers is still a real number and remains on the real number line. Linear operations on matrices include matrix addition and scalar multiplication. Linear operations on vectors include vector addition and scalar multiplication. For the imaginary number, we cannot obtain it through linear operations on the real number axis, meaning it is linearly independent from real numbers. Linearly independent means that the imaginary number lies on a number axis perpendicular to the real number axis. The complex plane is a mathematical concept that allows us to visualize complex numbers. It is a two-dimensional plane where the horizontal axis represents the real part of a complex number, and the vertical axis represents its imaginary part. Each point in the complex plane represents a unique complex number. This visualization tool is especially useful in understanding operations on complex numbers, such as addition, subtraction, multiplication, and division. Additionally, the complex plane provides a geometric interpretation for complex analysis, a branch of mathematics that deals with complex-valued functions. If we think of complex numbers in terms of vectors, we can represent a complex number, a plus b times I, as a combination of the unit vectors j and I. Here, j is the unit vector of the real number line with a length of 1 unit, while I is the unit vector of the imaginary number line with a length of I units. If we define the length of the vector as r, and r equals the square root of a squared plus b squared, then according to trigonometric functions as shown in the figure, a equals r times cosine theta, b equals r times sine theta, therefore, the complex number c equals a plus b times I can be represented as r times the quantity cosine theta plus I sine theta. Taylor's theorem, also known as the Taylor series, is a mathematical concept that allows us to approximate a function as an infinite sum of terms. It was discovered by the English mathematician Brooke Taylor in the 18th century and is widely used in calculus, analysis, and other areas of mathematics. The theorem states that any sufficiently smooth function can be expressed as an infinite sum of terms, where each term is a polynomial of increasing degree in a given variable, centered around a specific point. The coefficients of the polynomial are determined by the values of the function and its derivatives at that point. Taylor's theorem has many applications in physics, engineering, and other fields. It can be used to solve differential equations, approximate solutions to complex problems, and analyze the behavior of functions in various contexts. We expand sine x, cosine x, and e to the power x into infinite series. Then, using formula 3, we substitute ix for x. Based on the calculation in the figure, we obtained Euler's formula. And when the value of theta is pi, we can obtain Euler's identity. Euler's formula is a mathematical equation that relates the values of the exponential function, the trigonometric functions sine and cosine, and the imaginary unit, which is denoted by the symbol I. The formula is often written as e to the power of I times theta equals cosine theta plus I times sine theta. In simpler terms, Euler's formula shows how complex numbers can be expressed using real numbers and trigonometric functions. It's a powerful tool in mathematics and has applications in fields such as physics, engineering, and computer graphics. The geometric interpretation of complex number addition can be summarized as the parallelogram law. The parallelogram law is a mathematical rule used to visualize the addition of vectors, including complex numbers. When two vectors are added, the result is the diagonal of the parallelogram formed by the two original vectors. In simpler terms, imagine you have two arrows pointing in different directions, representing two vectors. You can draw a parallelogram with these two arrows as two adjacent sides. The diagonal of this parallelogram represents the sum of the two vectors. The parallelogram law is a powerful tool for understanding vector addition, and it has practical applications in fields such as physics, engineering, and computer graphics. Polar coordinates are a way of representing points in a plane using a distance from the origin and an angle. In other words, instead of using x and y coordinates, We use a radius, distance from the origin, and an angle, usually measured counterclockwise from the positive x-axis. This can be a useful way of describing complex shapes or patterns, as well as for calculating distances and angles in a two-dimensional space. Based on Euler's formula, a complex number c, which is expressed as a plus b times I, can be represented as r times e to the power of I theta. As we can see from the diagram on the right, a complex number c can be understood as a vector on the real number line with a length of r, rotating counterclockwise by an angle of theta. According to the above calculation process, the geometric interpretation of complex multiplication is rotation and scaling. Based on the calculation process, complex multiplication can be interpreted geometrically as a combination of rotation and scaling. This means that when we multiply two complex numbers, such as C1 and C2, C1 acts on C2 by rotating its vector counterclockwise by an angle of theta 1 and scaling its length by a factor of r1. Multiplying a vector by I has the geometric interpretation of rotating it counterclockwise by 90 degrees.